Hello everyone, today I'm going to talk a bit more in detail about re-entry and heat shielding optimization and why the grid fins are different on the different cores of the Falcon Heavy. However, first of all I would like to say thank you to everyone supporting me and everyone who has subscribed to this channel, because today we have passed 10,000 subscribers and I usually don't give too much about round numbers within the basically arbitrarily chosen decimal system. But I get that this is pretty big, and I'll make some sort of special, although late, because right now the Falcon Heavy launch is coming up, still scheduled for February 6th, not yet delayed from that, and probably happening on February 6th or February 7th at around 18 o'clock GMT. There's a lot of stuff to talk about, a few simplified model kind of reverse engineering studies I'd like to make before then, and generally there's a bit of a list of videos I'd like to do before then. Plus, I'm busy otherwise, so I don't really have the time to do this additional video right now. So for now, let's get to it and talk about the grid fins on the Falcon Heavy and why they are different, and especially why they are different this way, because on first glance they might seem reverse. It is a bit weird at first look. The left and right booster will be doing the typical return to launch site landing at Cape Canaveral landing zones. They now have 2 landing pads at Cape Canaveral, and there they will land, and it's pretty much standard. And they are equipped with these fancy heat-resistant titanium grid fins, which you can see pretty clearly. They are not really painted, they are bare titanium, and you can see that dark titanium against the white otherwise coating of the booster. Whereas the center core is colored white, and that is white paint on aluminum, which is of course much less heat resistant than titanium, although the center core is actually going to re-enter at quite a bit of speed. It is the Falcon Heavy, it is a Falcon 9 boosted by 2 additional Falcon 9 boosters, so the center core will go much faster than any Falcon 9 first stage has gone before. And you'd think at first that its re-entry would thus be incredibly harsh, and so it would need the most heat-resilient grid fins. Now, as for the left and right booster, that is pretty simple. They have titanium grid fins, they need titanium grid fins. The titanium grid fins have been developed after some trouble had occurred exactly with these return to launch site re-entries, because they are very steep, obviously. The booster kind of flies back and slows down and more or less vertically drops onto the landing pad with a little lift or orbital mechanics playing in, and so it's a very steep re-entry, which makes it a very rough re-entry. It quickly descends into the denser layers of the atmosphere without enough time to actually be slowed down, and thus in these denser layers is slowed down very rapidly and heats up very rapidly. And during this, it was on earlier launches that the aluminum heat grid fins would get a little bit too hot and pretty close to basically melting off the rocket, which would be catastrophic for the reusability aspect. But why, when the left and right core need titanium fins, does the center core get away with aluminum grid fins? And that is actually a bit tricky, because they are not bare aluminum, they are covered in paint, and that paint has ablative properties. The paint is actually melted off on purpose, and this melting process helps cool the fin down. And this is the more viable way to cool your grid fins at this type of re-entry, because it's a very different optimization goal. It is at high speed but with less dense air, so it's high temperature but a lower amount of actual heat, which also kind of explains the different coloring, and that's actually pretty tricky. While it does have manufacturing reasons, like the titanium grid fins just being bare titanium and the aluminum grid fins being painted anyways, it does make sense, because during a steep but relatively slow re-entry with a purely radiative heat shield, you would want it to be dark so that it can radiate away heat very well. At the same time, you don't have to worry too much about it absorbing heat from the air, because much of the air streaming around it is actually relatively cool, and you're just worrying about the heat vent itself overheating after absorbing a lot of energy very quickly, and you want it to radiate that off so that the grid fin itself stays at a sustainable temperature for titanium. Meanwhile, the grid fins on the center core are all different. They are going to re-enter fast but shallow, and they are going to be cooled ablatively, which means that the upper layer or the paint will ablate away to get rid of the heat. Essentially, the upper layer absorbs a lot of heat, and then it is gotten rid of, and thus the heat is gotten rid of, which is how some of the most used heat shields work. For example, the Soyuz, the Apollo, and most deep space probes that enter planetary atmospheres. Another advantage of ablative cooling is, of course, that you can sustain pretty much any speed and any outside temperature, even if you build off a relatively low heat resilience material, because the ablator itself isolates against the heat and at the same time gets rid of it by being ablated away, which means you don't need a material at all that can actually sustain the impact temperature of air at that speed. That temperature is actually not as much affected by the density of air as the heating process itself is. Less dense air has a slightly higher thermal capacity, but still you are dealing with that speed, and you can assume that a thin boundary layer, or at least the more blunt parts of the grid fin, essentially bring air to a full stop. So all that energy is turned into heat right within the air, and that with the air's thermal capacity gives you your peak temperature, but that peak temperature is only in very thin air, so while you need a surface capable of withstanding that very high temperature, be it by ablating or by being incredibly heat resilient, you don't actually absorb a lot of energy because the air is very thin, and so most of the heat, except for the very thick blunt parts, is usually just carried away by the air rather than conducted into the actual surface. This, together with aesthetics, also kind of explains the white color, because that means you get to absorb less heat. Of course, it also radiates away heat much less, but that's not the used cooling process here anyway. The air around it is too hot to properly radiate away heat anyways, and you have the ablation to get rid of heat, and so you just want to avoid absorbing any heat you don't have to. And since the main bulk of the actual aerobraking is done by the fuselage itself and not by the grid fins, they are pretty efficient at hypersonic speed, and so they don't cause too much drag. And so as long as they don't absorb too much heat from the air around them, they actually don't take in too much heat, which means they can get away with a relatively thin layer of ablator compared to any actual ablative heat shield that is used for actual aerobraking by itself. Of course, the actual braking mechanism applied, the use of the engines and the bottom of the rocket, as well as the use of gases from the engines, not just to slow down the rocket as any retro-fired rocket engine, but also as a heat shield themselves, is kind of interesting and another topic for another video. And at above Mach 10, this fastest Falcon Heavy first stage re-entry ever is one of the points I am a bit more worried about in my risk estimates, besides the parallel staging and max Q. Again, the Falcon first stage re-entry is quite complicated, and I am excited to find out how well it will fare at these extreme speeds, although the core will of course somewhat slow down before actually re-entering the atmosphere using its rocket engines. It's still gonna be the fastest core re-entry ever, and in my opinion the most likely thing to fail, if anything at all, although of course this would not compromise the Tesla reaching orbit or Mars. This is just the reusability secondary goal. A slightly more precise analysis of if the Falcon Heavy fails, what might be the most likely point of failure is still in the making, but for now I hope you understand why the different colored grid fins seem reversed on the Falcon Heavy, and what this has to do with re-entry optimization, heat shield optimization, thermodynamics, and the material limitations. In other news, today a Falcon 9 planned to be expendable has managed to perform an experimental landing which did end in the ocean because there was no drone ship, but actually remained somewhat intact. This is kind of interesting and somewhat unexpected, but it's actually not that incredibly relevant, so I'll cover that in more detail after the Falcon Heavy. And as always, thanks for watching.